I wanted to go over question 12. In particular, I wanted to go over the how do you compute the residual, and you might feel better to know that I've done this a few times and made several mistakes. So I think I've got it down now. So I'm going to work through this, and I hope it's helpful. So we've got a book about statistics used to judge a baseball's potential and baseball player's potential and a team's ability to win games. So we have a model here, a linear model. The winning percentage y hat is predicted by this slope multiplied by on base percentage minus this y-intercept. First, let's start by interpreting the slope. So we know that the slope in this linear model means the amount of increase or decrease in the response variable for a unit increase in the predictor variable. The predictor variable is on base percentage, so any of these that say a point increase in winning percentage can't be right. So so B and D, those cannot be right. We also know that it doesn't make sense for the winning percentage to decrease since the slope is positive. So let's find for each percentage point increase in on-base percentage, the winning percentage will decrease. No, that's not right. For each percentage point increase in on-base percentage, the winning percentage will increase. On-base percentage is the predictor. Winning percentage is the response variable. Choose C. That is correct. All right, let's continue. For this baseball season, the lowest on-base percentage was .315. The highest on-base percentage was .366. Does it make sense to interpret the y-intercept? Well, let's suppose a team had a on-base percentage of 0. Probably not going to win many games. But notice if x equals 0, their winning percentage is negative .4871. That doesn't make any sense. So it doesn't make sense to interpret the y-intercept. One cannot win negative 48% of games. Would it be a good idea to use this model to predict the winning percentage of a team whose on-base percentage was .240? Well, that's a smaller percentage than the smallest percentage of the data set that we're using, so no, that would be a bad idea. We should not use this model on that team. A certain team had an on-base percentage of .326 and a winning percentage of .548. What is the residual for that team? And then we'll have to interpret the residual. So, just get a new page up here. The residual is the observed value minus the predicted value. So the observed value is given to us as winning percentage of 0.548. The predicted value is what we get when we substitute in this on-base percentage to the model. So y hat equals 2.96 times the on-base percentage that we're given. I'll make sure I write it down right. Minus the y-intercept, which is 0.4871. Now I will whip out my handy-dandy calculator. 2.96 times 0.326 equals that minus 0.4871 equals 0.47786. So we have the observed, we have the predicted, we subtract. 0.548 is what we observed. The model says we should win this percentage of games. 0.548 minus 0.47786 equals 0.07014. The residual to 4 decimal places is 0701. 0.0701. Yes. There's the residual. Now, what does the residual mean? Well, let's think about that for a moment. The observed winning percentage was 0.548, or well, as a percentage, 54.8%. That's bigger than what the model predicted, which is somewhere around 48%. So that difference, the residual, that means that this team is above average. But now we have to pick out the correct version of that statement here. This residual indicates that the winning percentage is above average. This is not right because it has to be phrased in terms of the predictor variable, which is on-base percentage. This residual indicates the winning percentage of the team is above average. That's true for teams with an on-base percentage of that. Yes, that is that is the best interpretation of the residual. So, there it is. I hope that was helpful.